Good evening, good morning, and good day, everyone. Welcome to the third session of the developer meeting, OCNS. And today I am very honored to tell you a bit about our project called neurolib, which is a simulation framework. First of all, I'm very happy and thankful to be part of this group. We're working on a very young and new project that's been around for a year almost. So it's a pleasure to be part of this group of much more experienced devs that I also know their work of and have studied their work as well. So I'm very happy to be here. And so I'm going to tell you a little bit about what neurolib is, and so that we're kind of on the same page, and then just dive into development related topics about it. So please feel free also to interrupt me while I'm speaking. Last few sessions, questions have come up in the chat. You can also just raise your voice. Actually, I would prefer that, but as you wish. So if you raise your voice, everyone else will also hear the question. Okay, so I'll share my screen. And I hope you can see my desktop now. All right. I've prepared just a handful of slides, so to give you an idea about what neurolib is about. And as you can see, so our tagline is easy whole brain modeling for computational neuroscientists. And so this is kind of the gist of what I'm going to tell you is what is whole brain modeling and why it's useful. I think it might make sense to talk about this because I know that many people here are working on single neuron simulators, and whole brain modeling is not that popular among simulation and modelers yet, maybe. So I'm going to tell you a little bit about the background here. Then we're going to look at neurolib, and then I'll tell you a little bit about what we're planning to do if there is time left. So I like this kind of plot. So let's look at scales in computational neuroscience. And on the x-axis, you see a spatial scale, and on the y-axis, complexity you could imagine is as the number of equations that you need to simulate, maybe in order to represent a system. And here on the lower left, this is a depiction of a point neuron model, right? We have heard about Brian, for example, which is a framework to simulate point neurons. And you can think of it as a closed unit with inputs and outputs. And there are also frameworks and research to simulate single neurons, but with a morphological structure. And this can get arbitrarily complex. Actually, you can simulate the whole 3D structure and divide it in more and more, higher resolution, which will make it arbitrarily more computationally hard to simulate these guys. And to the highest level of doing this is probably what, for example, the Human Brain Project people are trying to do, which is to actually simulate a whole bunch of these guys together. And these problems usually require supercomputers, so kind of insane infrastructure. And moving further to the larger scale, we have neural networks, so networks of these guys now, and then the complexity drops sharply, but the scale increases, which is where our work starts. And this picture is there to represent neural mass models, so mean field models that just reduce a whole lot of complexity by disregarding most of the dynamics of the individual neurons, but giving you a very, very fast and efficient way to simulate and represent the population activity of a network, for example. And then cranking up the scale again, we can then put these guys together in a network to represent the largest system. And this is probably the largest neural system that we usually look at, which is the whole brain. And this is where neurolib lives, basically. Okay, so why is whole brain modeling useful at all? I think it makes sense to ask this in the beginning. So most research revolves, much of the research revolves around this question of, what is the structure-function relationship of the whole brain? Because nowadays we know things like the connectome, and we can then ask questions. What happens if you take out one connection between two brain areas, for example? What happens if you change the delays between brain areas? How is the dynamics of the brain related to graph theoretical measures of the brain, and so on. So you can imagine these kind of questions become relevant. At the same time, most commonly used recording modalities, they record not only a single neuron activity, but large regions of neurons. EEG and fMRI can only resolve so much. So there is a kind of a natural equivalence of trying to represent neural activity as a population itself, because we cannot, in many cases, cannot see clearly what's happening. So in this context, it also makes sense to use whole brain models to explain this data, especially if it spans across the whole brain. We can then now start also ask questions about, if you represent these systems, you can also start asking what happens if you perturb the system. So one popular application of this is to simulate electrical stimulation of the brain, which is a very simple method of basically putting electrodes on your scalp and just pumping low current electric fields there through it. And we can also do that in a whole brain network, obviously, by adding inputs to the brain regions that we're simulating. And another thing is that, which is also something very new coming up, is to ask, why does the brain's dynamics look like it does, depending on certain neuromodulator maps that we might have from of the brain. So, for example, there are maps of serotonin expression across the brain, and we can then scatter these maps as parameters across such a whole brain network and ask, how does this affect the whole brain dynamics? And finally, this just gives us a mechanistic model to study brain dynamics. So we're not just limited to studying data from recordings, but actually change parameters, see how it affects things, and ask these more fundamental, maybe theoretical questions of how do oscillations in the brain come about, how do waves spread in the brain, and how do certain measures of dynamical states, such as criticality, affect the dynamics that we can expect or see in the brain. So this is the context of why this is all relevant and happening, basically. So at the heart of whole brain modeling, there is the network information that we need about the brain. And this is usually nowadays recorded, measured by DTI. This is diffusion tensor imaging, an amazing magical method of getting the fiber connectivity in the brain. So basically what this gives you is, very briefly said, DTI gives you a tensor for every point in space in your brain, and this tensor tells you how much water diffused at that point during the recording time. And it turns out that water flows more easily in the direction of a fiber than across the direction of the fiber, right? It's like a tube, basically, transporting diffusing water. And then if you start connecting these tensor components, for example, here's an example, then you get these streamlines. And these streamlines are basically the axonal long-range connectivity in the brain. And so you can get something called the connectome, which is, I think, referring to the genome as something unique to a person, something like a fingerprint maybe. But well, it also tells us how different brain regions are connected to each other. And so one step on top of that we need to do is, now that we have kind of like this fiber bundle, 3D fiber bundle, we also need to define brain areas. And you probably know that the definition of brain areas is often very arbitrary. Also in whole brain modeling, there are different maps. We call them atlases, where we divide the brain into brain regions, and then given the connectivity and the definition, the volumetric definition of what a brain region is, we can then start counting fibers. And that's basically what we do. We simply count how many fibers go from region A to region B, which gives us these adjacency matrices. This is now the actual representation of the brain network in the software, which is you have the number of brain regions here in X and Y, and then the color tells you how many fibers have we seen passing from A to B. And also we have the information of how long are these fibers on average. So here, for example, you would see one brain region, let's say you start here in the frontal cortex, and would be left, right, left, right, left, right, going through all the regions. And this gives you how long the fibers are between. Okay. So this was the structural part. This is the information that we need to put into brain models. Another that I just quickly skimmed over was we also need a population model to put now in every brain region. And we use usually neural mass models for that. We could, in principle, also use spiking neurons for that, but that would be just, just making everything n times more harder to simulate because we have n brain regions now. What we do instead is, and this is the only picture that I'm going to show you in this context, because a picture probably tells you more than anything else I could do in this short time, basically using mathematics to reduce the left-hand side where you see a detailed network of spiking neurons just to something that is much more coarse-grained, but has only a couple of equations left, but gives us the firing rates basically of the population. And we have done this in our lab, and there are other people who have done this a lot, and we have also verified that this actually gives us the same bifurcation diagrams between spiking neurons and neural mass models. So we're fairly confident that in this case we use adaptive exponential integrated fire neurons. We're fairly confident that this representation in neural mass models is fairly good if you're only interested in these macroscopic properties like a population firing rate. So are there questions up to this point? Because this was kind of a dense primer. If not, I'll just go on. So again, a picture instead of words, just putting everything together basically, and combining these two things, the structure information and the neural mass model, we get a whole brain model. Simple as that. And from the whole brain model, we can then extract, simulate it and extract data, which is, for example, firing rates of every single brain region here in different colors. The black trace is something like an average. And then we can take these firing rates and convert it into a bold signal. And bold signal is blood oxygenated level dependent signal, which is what the fMRI scanner is recording. So the brain activity in an fMRI is usually the bold, the oxygen response of a brain, and there are models to convert firing rates of neurons into bold signals. So why would you do that? It's a very bad signal, but you need to do that if you want to compare basically your model to real data, which is bold data that we have. So in this step, when we have a model, then we can start optimizing it or explore it and compare it to actual data from resting state fMRI, for example, which we need to do with bold data. So this is just a visual overview of what the framework does. And this is, yes, please, yes.
How many neurons are taken in one population, like for the
so it's a very good and important question. In this case, so when we do the mean field limit, we assume infinitely many neurons per population. So theoretically speaking, there are infinitely many neurons per brain area, so that the theory works. But in practice, you could say that these models start working at a couple of thousands of neurons. They become more and more accurate the larger the network is, basically. So, but I should add, we are not simulating individual neurons. We're only simulating their statistical overall behavior. So okay. I hope that was clear.
Yeah.
Okay.
So does it also depend on the length of the fiber? For example, like how many neurons are close by to each other? So they are taken in one population and neurons which are far apart.
The distinction of what is part of one brain area, for example, and not and part of the other is done at the part where we define the volumes of the brain. So when I showed you an atlas, basically this is where we make the decision of this is one group of neurons and this is the next group of neurons.
Okay.
Okay.
Thanks.
So here's one example, just a time series I wanted to show of what the output of a model looks like. You can see in the top panel, it's an average firing rate. We were interested in simulating sleep oscillations here. So very slow oscillations. This is over a course of 60 seconds. And the middle panel shows you the activity of 80 different brain regions here. Yellow is on and blue is off or low activity. And you can see here although there's a lot of fast dynamics that you cannot see, there's also very slow dynamics that I'm trying to show here. And if we zoom into one of these events, for example, where many brain areas go into this down state, we can see some kind of a structure. And in this case, it's kind of a wave that propagates in the brain, for example, from the front of the brain to the back of the brain. So these are the questions that you can then start to ask when you have a brain network model that works. So the last eye candy I can share is what I just showed you basically in an animation. So here you can see the brain network doing its thing in real time. And you can see the different brain areas lighting up here and signals being transmitted by these fibers that we have seen before to other brain areas, giving us kind of a complex interaction. Okay, so to briefly cap, I said that neurolib is a very young project still, and it has a short, maybe interesting history. And why we came to make this library, it wasn't a plan in the beginning to make this library, but it was basically kind of legacy code from our group because people have been working on these population models. But that was when I joined still MATLAB code. So that was obviously hard to work with. And at some point, me and others started to port this to Python because we like Python and made, once you have one model working alone, you can, generalize this easily in code to make N of these models and just connect them up. So the next step was not so hard to make a whole brain model out of a single neural mass model. And then we were just working on whole brain modeling for a long time. This is an ongoing project in our group, but often we needed to share code. So I shared my code with students I'm supervising, and every time I felt kind of bad because everyone knows how scientist code looks like. If you don't need to share it, it just works, but not much more basically. And this was the case also for my code. But then we also came to a point where we needed to publish code, and this is where it then starts to get, a bit more critical, that you actually write code that is maybe worth looking at. So out of this culmination of necessities, we decided to build a proper Python library, which then became a whole framework, not only for simulating, but also for optimizing and exploring. I'm going to show a little bit in a second. And very recently, we've also written and submitted our first paper, methods paper about this framework, where we just demonstrate its capabilities and talk a little bit about it. And if you're interested, you can ping me later and I'll show you where you can get it. So with that, let's just go into the GitHub repository. Yes, so here's our GitHub repository. Most of the information in the beginning was actually crammed down in our GitHub README file, where everything is described for beginners. And so I think it makes sense to maybe just have a look at the project layout here for a second. So this is the library main folder, and we have a subdirectory called models where we put all the models in that we implemented. We have a subdirectory called optimize where we put in mechanisms for optimizing models using different algorithms. We have some data in there, the data that I've showed you, the structural connectivity matrices, etc. So this is sample data to just get going. And then lots of utility files. So this is not even that much integrated into the framework, but rather you can load them separately and have fun with them. And probably most importantly for usability is our example directory. And I'm going to show you some examples in a bit. So let's have a look at our example directory. And as you can see, all of our examples are Python notebooks, IPython notebooks, Jupyter notebooks, sorry. And I will show you just a couple of examples so you see the syntax and everything. But maybe before I do that, I can show you just this one last overview of the project structure again, how things are connected to each other in neurolib. So we have the simulation module in the center here, which is called the model, where we load different models and we put in empirical data into that model. Then we simulate it. And here's with a certain function called autochunk that I'm going to tell you a little bit about later as well. Then we have post-processing functions, and outside of this whole box is the exploration and the optimization module. So neurolib itself can already explore models, meaning explore its parameters, and optimize, meaning find parameters that match the data the best. Okay, so if there are no questions up to this point, I'm just going to dive into an example. So what do we do here? These are the example notebooks I was talking about. And when you want to run a neurolib model, you basically do this. So you import a model. We don't import everything at once, but just the pieces that you need from the framework. So you load, in this case, it's called the ALN model. This is our poster model, and some functions, for example, for later use as well. And we instantiate this model. It's as simple as saying, this is what I want. And there are no arguments here in the constructor, meaning that is one single brain region in this case. And then we can change parameters of the model. And the parameters are part of a model. And there are attributes here, dictionaries, very simple dictionary. And we can just change the parameter of this model by putting dot params and then change the duration, for example, like here. We overloaded this dictionary with a couple of other functions. For example, for lazy people, you can just do this dot notation because it's faster to write. Basically, it's just interoperable. And here in this example, we add noise. And in this case, we simulate an Ornstein-Uhlenbeck noise process where you can set the amplitude of the noise. And that's it. So we have loaded the model, we've changed parameters, and then we do run. So let's do that. I have to start up here, change the directory. And so this will take a while until it's initialized, but the actual model creation and running, so for 10 seconds, takes literally a couple milliseconds only. As you said, that's done. And then if we want to look at what we just simulate, we can simulate now the results are stored in certain keys of the model or in an output attribute here, and we can just plot it. So we plot the time here, now the simulated time against the simulated activity. So this is now we have a excitatory and inhibitory neural population that are doing this. So the EI oscillation that everyone knows about is basically this plus some noise. And so we were talking a lot about what a model can do, but let's just jump right ahead to how you can simulate a whole brain model now. And it's again as simple as we could think of making it. So you load this dataset class, which manages now empirical data. So this can load the empirical structural matrices that I've showed you before. And we load a data set called GW here. In this case, we have also one other human connectome project data set here. We load it. Now, instead of just loading the constructor by itself, we pass now a structural CMAT. This is the connectivity matrix, and the DMAT, which is the delay matrix. So these two data matrices, we use them, we change some parameters, and now this is a now we have created a brain network with actually 90 brain regions, and these brain regions are defined by these matrices. Add some parameters here and there. These are the matrices, and then just simulate it like we've done. So dot run. I have told you before that we have this thing called chunkwise, and it's kind of pretty neat way of integrating numerical ODE systems. It's very simple, actually. It helps you to save RAM, and it does that by throwing away most of the data, basically. So if on whole brain modeling, you're often interested in very long simulations, because when you want to compare to an fMRI scan, for example, you actually need to simulate for 10 seconds. And the neural dynamics is on the order of 0.1 or less milliseconds. That's the integration time step of the neural mass model. Then you want 10 minutes of data and bold data. So it would be insane to simulate 10 minutes and keep it in RAM and then convert it to bold. That just wouldn't work, which is why when we simulate chunkwise, we say this is the amount of time that you want to simulate, and then we chunk it into slices and simulate only one chunk, and then remember the last part of this chunk and throw everything away that we don't need and use this as an initial condition for the next chunk. So it is basically doing this chunk by chunk by chunk. And at the end of the day, you only keep what you needed. So you say, I want bold, for example, it will simulate bold while doing these chunkwise integration steps, and just keep the bold, for example, and throw away all the firing rates, which would otherwise take up gigabytes of RAM. At the end, you just end up with the bold data that is has a very slow, low sampling rate. So this enables us to run these crazy long simulations on a normal laptop, basically. And so, yeah, this is how you load a model and how you simulate it. And I'm going to show you later how you would write an own model yourself. But before that, I also want to show you two other different important parts, which is the parameter exploration and the parameter optimization part of the framework. For the exploration part, it does basically, it's very simple. Every model has parameters, and usually you want to know how the model behaves when you change certain parameters. And the easiest way of finding out what it does is to just simulate every single combination of parameters that you are interested in. And with neurolib, it's very easy to do that. So I'm just going to import everything here, and it's I'm going to show you a toy example. So we're not looking at a neural model here, but something now will explore this function. It's not a neural network or anything, but the function, which will do nothing more but to compute the distance to a unit circle. So it has parameters, which is x and y. So in the space, a point, and then the value of that point will be simply how far is this point away from a unit circle. We define this function, and we load this object called parameter space, which is also part of neurolib, in which we can then define ranges of what we want to explore. So let's do that. 1 second. I'll define this function. I define the parameters I want to explore, and I initiate this box search object that is also now handling everything for you. Basically, you put in the function that you want to put in, or the model. You tell which parameters to optimize and where you want everything to be stored. And now this uses another framework in the background, which is called Pipette. It's a parameter exploration toolkit, which is much more generic than what neurolib can do. That handles the parallelization and data handling for us. So I'll start that and go. So lots of things will happen here now. And if we look at my CPU, actually, I was hoping that Python would use most of my CPU now in parallel, but Zoom is actually using more. Okay, so we did 400 runs now of this model, of this toy example. And let's load the results. So this now loads everything from disk, what we just simulated. The idea is that this would run for a long time on some server, for example, and then you will come back and load the data, look at the results now. This is X and Y, all the parameters that we changed, and then the distance that was calculated in this function above. And if we just plot this, we get what we put in, basically. Here's the exploration of the circle. Okay, so now, again, I just want you to imagine this is a toy example, but your model inside here. And these are the parameters. The axes are the parameters of your model that you're trying to change. And with that, I'll just skip to evolution, to optimization. And the optimization in neurolib uses an evolutionary algorithm. That has a reason, mainly because evolutionary algorithms are extremely versatile. You can throw anything at them and they will kind of deal with it. They don't need an explicit computation of your Jacobians or some other heuristics. It just simulates many individuals. It's called in evolutionary optimization, with different parameters, and if they are good, they can have sex and have a child. That is a new parameter combination, and this is just repeated in generations after generation after generation. So I have a little picture showing this as well. So this is just a overview what evolutionary algorithm is doing. So you initialize your population. This is now a population is a set of parameter combinations. So it could be like 100 different brain network models with different parameters. Then you run all of them once. And then after you run them, you select the ones that are the best. They become to be the parents of the next generation. So you take them, the best ones, and then you mate them, which makes one new or two new offspring, which has now parameters that is related to the parents. And by doing this iteratively, you get better and better and better. And at the end, you end up with a model that is good. So again, I want to show you how easy it is to set up. I accidentally started it already. So we again optimize not a neural model. In this case, we want to optimize a circle again because we like the circle so much. So in this case, the output of this optimization will be, again, how far you're away from the circle. And the idea is we sample from this 2D plane different parameters, and we hope we can get onto that circle as close as possible, basically. And here, the distance to the unit circle gives you how fit you are. And we do that. So we again use parameter space. We tell it the variables the parameters to optimize, their ranges that we want them to optimize in, and then set some parameters of the evolution. For example, how many individuals do we want? How many generations do we want to run this? And we run it. And this has run for quite a couple of rounds already. And it should be finished. It is finished already. And then we can, again, like the exploration, load the results and then print some information. And we should see here, nice. So this is, we started basically, now here you have, again, the same space as I was showing you before, X and Y axis. We started with the uniform distribution of these dots, individuals, basically, with different parameters. And they slowly, during the evolution, converged onto that circle because the circle is the optimal point where they want to be. And again, In a neural system, you can think of this again as your neural model parameters, but the optimization would usually be some kind of fit to empirical data. So you want to find the parameters that make a model that reproduces empirical data the best. Okay, so again, we're back at the GitHub repository. And I just want to use the remaining couple of minutes to talk about how we develop and what kind of methods we use to organize things. And first of all, very recently only, and I'm very happy that that I can show you now, is very recently we got a documentation up, actually. So the only documentation that we had up until now was the examples that I showed you before and heavy commenting of code. The idea of neurolib is not that you use it, basically, just you download and press play, but the code is written such that you go into the code and make changes. So there is no user interface. The code is the user interface in that sense. That's how we look at it. And that's why we commented the code as much as possible. So if we go to the documentation, this is again the README. And now we have the different modules. This is created from the doc strings of the different functions. And for example, the box search, which is what we have used before, has a description of what it does. And I want to, so we also convert all of our notebooks into this, also put it into the documentation page, as we've also seen in Brian. I think we're using NB convert for that, which converts the notebook into a markdown file, basically. And I want to use this opportunity to show you one example, which is the example that shows you how to implement your own model, basically, in neurolib. And so this text just describes what's happening. I'm just jump to the code in a second, but this is basically the very simple equation of the model that we want to implement. This is a linear model. It tells you, activity decays exponentially, except there's input, then it increases. That's basically what it does. And this input comes from other brain areas. It's the most simple brain network model that you can build. And the code to implement this is summarized here. So this is basically all that you would have to write for that. And there are certain boundary conditions that you need to adhere to so that neurolib can work with the model. So if you want to write a model, you write your own class, and that class inherits most of its functionality from this superclass called model. And you define your state variables that this model has. You define the initial variables, the initial values of this model. And then you tell the superclass what is the function that I need to call to integrate this thing. And now what is particular about neurolib is that neurolib doesn't do the integration for you. You actually need to do the integration yourself. This has a reason that I'm going to talk in a little bit about, which means though you have to write the Euler loop yourself, or any other integration that you like more, maybe. So in this case, we define this function as the integration function. This does just some mumbo jumbo preparation of variables, but eventually calls this thing ngit integrate. And now here's what the magic of the whole thing is. Basically, this ngit integrate is a function that is accelerated with number. Ngit, JIT is called, is a just-in-time compiler. And if you don't know number, I strongly urge you to find out about what number is. It might save your life one day. Because integrating, doing simple loops like here, what we do here is very simple. We just loop over time, then we loop over nodes, and we integrate our equation that I've showed you before. And doing this in Python would take you pretty much 1,000 times longer than doing it with Numba. So Numba takes this code and generates C code from it, which can then be run much faster than any Python code could run. So this is basically it, how you would implement a model. Are there any questions about this part? Okay, so adding new features and everything. I mean, obviously we're collaborating here. Most of the PRs and code has been written by Nicola and me, and who's also in our group. Others in our group are also adding their smaller contributions. But neurolib has been around for only a year. In that time, I'm very happy to receive actually random emails from random people that just want to use it or for their student project or whatnot and have questions about it. So I think people are starting to hear about it, and hopefully we'll also get more contributions from outside of our group. And we're very happy to receive them, obviously, through the usual means of contributing, which is forking the project and doing a pull request. And we even when I do a feature completely by myself, I learned to appreciate this very strict procedure of doing a pull request, then running all the tests, and not even the admin is allowed to merge without the tests being all green. So we're giving us time, and we're discussing even small changes between us, which makes everything a lot more manageable. At least for me, I cannot imagine anymore working on a project that is not integrated in a workflow, and especially when it comes to continuous integration. So a couple of days ago, we actually had the first person to write a post in this GitHub discussion asking a pretty direct question about how to use a model that they're working on. So I was very happy about that. And speaking of tests, we had this small discussion before in the work group GitHub forum about I think Joe raised this question, if I'm not wrong, about what testing environment we're using, and we started off also with Travis. I liked to use Travis because they have a nice business model. Where they say open source is free, everything else is paid. And also they actually live here. They are in Berlin here, so I like the idea of knocking on their door in case something went wrong. But in the last month, we transitioned to GitHub Actions now, and we'll probably never look back. And I must, just naively or briefly say I just like it a lot more. It is much faster. You can spin up 10 machines at once, and it takes a couple of minutes until everything just starts running. And in our case now, if I go to the actions part, so we do testing for every single push that we do. We do additional testing for every pull request that is submitted. Then let's look at one of the tests. And we have now 3 types of tests, which is called CI, continuous integration, as looking for bugs. Then documentation is also built upon each pull request and merged into master. The documentation is updated because most of the documentation comes from the source code itself. So it needs to be updated on every update of the code. And then we have another routine that runs all notebooks every time we do a change. So we are sure that all the examples still work whenever we do a change. And obviously, I mean, this is just, it wouldn't be possible to build this project without this rigorous testing all the time, because always something breaks that you wouldn't have thought that it breaks if you just change something here. And okay, so whole brain modeling. I've told you a lot about whole brain modeling, how it works, why it's useful, and you might wonder, is there other software that can also do this? And you would be surprised that actually there is only one. The other project that does whole brain modeling or focuses on whole brain modeling is the virtual brain. I think so. The biggest difference between the virtual brain and neurolib for sure is the lack of graphical user interface for us. So the virtual brain is trying to be, and this is I mean, I'm very grateful for this, is trying to be accessible for also people who don't program. And this means that you can start, you know, a whole brain model and click it together basically with your mouse and see the results immediately. So it does that very well. And you can just get going without knowing too much about what's happening in the background. Obviously, we have a very different goal. So our project is more, you know, made for hackers, kind of people who are not afraid of looking at the code and changing it. That's what I mentioned before. And also the optimization and exploration parts was just, you know, we had this from the very beginning, and it's a central core of our project, which is lacking in the virtual brain as well. But the virtual brain also has a Python library. So it doesn't mean that you can't do these things with the virtual brain. You just need to build it around it, some kind of optimization infrastructure or something. You have to build it yourself if you want to do it. However, I think for us simulators or modelers, the most important or interesting difference is maybe actually the speed or the computational efficiency between the two frameworks. So when I first heard of the virtual brain, they were actually running on pure Python, which, as I tried to tell you earlier, makes things around 1,000 times slower than we're running it right now. Then they also started at some point to use just-in-time compilers for their code, also Numba. And so I'm reading their code also for, you know, learning about how to do things. As I said, I'm sure they're doing most of the things a lot more, you know, rigorous than we. So here's an example of a linear model that they have. It's the same thing that I showed you before, and the biggest difference here is now in the virtual brain, you don't write the integrator, you write the derivative. So you pass the derivative to the integrator of the virtual brain, similar to SciPy's integrate, for example, and that would do the integration for you. And this is obviously, I mean, this is much better for a user, because you as a user don't have to care about, you know, stiffness or all the problems that come with numeric integration. It will do it for you. But you can see it's a Python function, so this is going to be terribly slow. And in newer versions of their models, they have also now, I mean, the framework itself is the same. You have to pass derivatives. But in newer versions of their models, they started using Numba as well to compute the derivatives of their models. So here's one so-called Hopf model. It's a simple equation. But now this is also a decorator for Python that now compiles this function. This is a very good start. However, now this is just information I want to, or research that we have done basically to find out what is this, why is there such a big speed difference? And the biggest reason is, although this will help you, you will still suffer a lot if your integration itself happens in Python. So what's happening in the virtual brain is you have Python calling a derivative that is C, and then doing integration, and then calling a derivative again and doing integration. So only this part is accelerated and this part is slow. And I mean, it is hard to actually make it other way around, because, you know, the nature of just-in-time compilation is that you have, you know, you have to close this part off from the rest. You have to compile a blob of code that just has to run for itself, and you cannot make it easily doing that and still communicating to some kind of integration engine inside your framework. So in neurolib, we have just all the integration, every loop is inside of this decorator, which makes things actually around, almost 20 times faster than if you do it this way. So this is basically the way we implement things now. I think I'm almost at the end of what I wanted to show you. Just as a last remark of what we are doing in the future. So obviously we have a couple of models already implemented here. So we have Fitz-Nagumo, oscillator Hopf model. We have a thalamic model, Wilson-Cowan, a Wong-Wang, and the ALN that I've showed you before. So these are all very popular neural mass models. And we're going to add more. And it's fairly easy and fast to add one, as I showed you before. So this list can grow fast, I think. But so our ultimate kind of milestone goal is something that I've also discussed with some people in this group before, unrelated to this work group, but I think it's a more general problem in building simulation frameworks, which is we're going to tackle, and we're already doing it, tackle heterogeneous modeling. And heterogeneous modeling means that now instead of having one model that lives on, let's look at this picture. So instead of having the same model that lives on every brain area, we want to actually simulate a brain where some nodes are one model and other nodes are another model. So a different model. For example, we would have models for cortex, which is this guy, but we want to simulate something else in thalamus or in hippocampus. And there are other neural mass models for these brain structures. One way of doing that is to be very inflexible, just to explicitly write down the loop, number compatible loop, that just loops through all cortical nodes and then loops through thalamic nodes, and then to do this explicitly, which would then give you a heterogeneous model. But in order to change it, you have to change the code and go in. So this is obviously not very flexible, but still a possibility, and we know it works and it's very fast. This is probably even the way that we are going to do things in case we need to run very long simulations, because this is just the fastest way of doing things. However, we want to also do it a bit more elegant, which is why we are working on something called multimodal. And this is Nicola is devoting most of his time or more time into this. Unfortunately, he's not here to talk about it today. But what multimodal now does is solve the following problem. You can imagine that if you have different models, let's say you have the ADEX model and you have a thalamus model, and you want to connect them, you need to tell the system somehow which variables from one model go to which variables from the other model. So where's the coupling? The firing rate of here goes into the synapses of here, for example. And you need to specify this. And you can do that. You could write this all in a beautiful Python class structure, and it would work. However, it would be slow because you couldn't accelerate it with Numba, as I showed you before. Numba doesn't know classes. It just wants a loop, and it wants to work on that loop. It doesn't want to work with classes. So one solution we came up with this is for this is to integrate both of these approaches, which is, if we go here into multimodal, there is something called the builder. Now we have different neural mass models, again, kind of the same things that we had before, but now we have different classes for different parts. So for example, you have an excitatory and an inhibitory class, and then this is the so-called, you could call it a K1 node, which is one population, two of these. And then we make one node of these things. So we say this is one node, this is a K2 maybe. So it's a higher hierarchy. And then we have, this is one brain area, and we connect it to others. And we say, okay, if we want 50 times of this node connected by these variables. And then we want two thalamic nodes. We instantiate them the same way using these Python classes. But now instead of simulating it using Python, what this backend can do is to take all the equations that are part of these models and actually paste it into a text template, similar as Brian does it for C code. But now in this case, it's actually Python code. It generates Python code that can generally, integrate over this whole mess of models, which becomes a huge matrix. And this Python code is a template, is pasted, and then accelerated using Numba. So these are the steps that we're going. Class structure that builds these, text file or text that comes out as Python. We add Numba engine to it, and suddenly it's 1,000 times faster. So this is basically what we're working on right now. And the feature, why we do this is basically because we think this helps you to just work much faster and to experiment much faster. And so you can just load different brain areas and add them to the graph without much hassle. But obviously, this is a very challenging problem. It turns out that it's just very complicated to keep tab of all the different nodes that you have to do the exchange of data and to do it in a fast way. Okay, I think that is it. This is all I wanted to share with you. I'm very happy, thankful that you had time to listen. And if you have any questions, please ask them.
I had just a general query about GitHub Actions, because I think from our discussion, everybody is sort of now looking and moving to them. What base images and things do you get on GitHub Actions? Like on Travis, you get Ubuntu 18, perhaps, on a 64-bit system. What do you get on GitHub Actions? Can you choose?
You can. So we're launching usually here a Ubuntu latest.
Right.
I just received notifications from GitHub that this will transition to Ubuntu 20 something.
Okay.
So a TLS version of it. And the macOS is also the newest.
All right, that's quite useful. Yeah.
Yes, and it launches a lot faster than than Travis.
Yeah.
And it's very easy to have these it's called matrix, test matrix in their lingo. So you would launch Ubuntu and macOS with 3 different Python versions, which makes you end up with 6 different runs in this case.
Okay.
And I can just also direct you to these files in our repository. I use them as templates for other projects.
I'll have a look there.
Yeah, it's very simple. You just set up Python, you install your dependencies, and then you go
so
with what you need to do.
Similar, then it's not very different from the Travis YAML.
Yes, it is YAML,
yeah.
Which means that 5 times out of 10 it fails. Because you have put a space somewhere.
Yeah, so. I know.
Yeah. This I should also maybe mention we also measure how well we test using coverage. I think coverage hasn't been mentioned yet in the talks before. So we have this thing called CodeCov. It's also pretty neat. You send the PyTest basically to CodeCov, and it tells you how much % of your code you have actually tested with your tests. And this is a number that you can maximize during development. And it's nice to have these things to measure yourself against. So our number is, we're trying to keep this thing above 90% basically. And it's, it's really just good to see that you have written, functions that you're not hitting with the tests, and this will immediately notify you about it in the pull request itself and give you a rating, and which you can use to improve on. Another thing that hasn't also been mentioned is we're using a code formatter. I can also recommend maybe looking into these things.
I was just going to ask about that. I noticed it and I was going to ask. Isn't Black quite aggressive though with code style,
Yes.
right?
I mean, it was a local minimum why we ended up here, but I have come to love it a lot because, as you can see, they also say they're the uncompromising code formatter, meaning that there's literally no room for discussion. And this is just, if you work with other people, I think it makes sense to have some kind of norms, and no one likes to enforce norms. It's much better if software does it for you. So if you have VS Code, I don't know which IDE you like to use, but you can integrate these formatters into your IDE and you press just save, and it will clean things up for you. So if I am someone who likes to write, oops, sorry. If I need to turn off my firewall. If you are someone who likes to write things with spaces in the argument, and then now I'm pressing Command and S, so I'm saving it, it will just say, no, you're not allowed to make spaces here, and just clean it up for you. And this is really, really nice. I can recommend looking into this. And
so just a question about that. Do you enforce that for commits, or do you have like pre-commit hooks or something like that?
No, until now we're just, we mentioned it in our contribution document here. There's nothing in the background that will check that. There's just a linter in the background that gives us some warnings and etc. But yeah, you have to set it up yourself.
Yeah.
I was looking into Number. So Number depends on LLVM Lite, which then depends on LLVM, right, for the just-in-time compilation.
That is true. Yes.
Yeah. Have you had any trouble with versions? Because I think LLVM Lite had come out LLVM version 10 came out recently, I think, and Number was still lagging. And this is generally not a problem for most people, but because I'm on Fedora, Fedora moves quite quickly. So we already moved to LLVM version 10, and Number didn't quite support it yet.
It's interesting. I haven't had any problems with that yet. I just know for macOS X, it was a bit more complicated to get it on the system that we want to test it.
Right.
But I think if you just install Number using pip, it will probably already tell you what to do.
Okay,
yes,
okay,
yes. Yeah, I mean, Number is not open. I'm not sure if Number is open source. LLV, some part of it is not open. So on this, in this whole stack, but I can really encourage you to have a look at it. They started as one of the few and many just-in-time compilers, but they're one of the few that actually survived, because I think it's probably very, very hard to build a just-in-time compiler and maintain it. And with time, they just kept adding features of NumPy into Number. So Number is trying to be NumPy compatible, meaning that if you do a np.multiply, it will actually not only do it in machine code for you, but even parallelize it whenever it can for you without doing anything. So Number apparently even does stuff on the GPU if you want it to, which I haven't tested yet, but maybe in the context of individual neurons where you have thousands of systems, that might make sense.
Yeah, no, that's definitely something worth looking at. Yeah.
I wanted to ask about that, but I mean, as Thomas well knows, for the GPU code, they always run into limits with the testing on the test servers, right? Because Github Actions doesn't run things on the GPU, so that's a really annoying thing. I'd love to have a solution except for paying money.
Where would you run GPU tests actually?
Well, you could buy. I mean, they're only, as far as I know, they're only paid options. So you basically rent a virtual machine. Rent a virtual machine running on a real machine that actually has a GPU, or you set up your own machine and connect it to your test infrastructure.
Yeah,
If anyone knows of a free alternative to run CUDA GPU tests, I'd be be very happy to know about it.
We run it all on our own machines.
Right.
The GPU stuff. Yeah.
Yeah, there's a teaser for our dev talk in a few weeks' time, how you set up CUDA testing on your own machines.
Right, nice.
Yeah, I think a lot of us are really looking forward to that, because that seems to be quite a common problem.
Yeah, yeah.
Because all of these third-party CI providers seem to have the same solution, which is you buy some CUDA machines on Amazon Elastic Cloud or whatever, and then you pay for your GPU testing time.
Right, yeah. If you're a company earning money with your software, then it's a perfectly reasonable thing to do. But
Yeah.
Exactly. I mean, I just love the state of things these days, that we expect servers popping up out of nothing for free. This is just a great time to be alive, to be honest.
Well, it's great how it works. Yeah, I mean,
Yes.
struggling with testing stuff on Windows and OS X and Linux and GitHub Actions or whatever. You just say, run the thing on.
Yeah, give me 10
Linux
for
OS X,
service for this little
Right.
code change that I did. Yeah. Okay. Any more questions? And if not, I'll stop my screen share at this point.
Well, that was great, Koglar. Thank you so much.
Thank you a lot for joining. And I think we can stop the recording probably, or
I will do that now then.
thank you.